Hello and welcome. This is day 9 of our journey, video journey to ace the interview. Let's begin our daily challenge. All right. Question 1061. Lexigraphically smallest equivalent string. It's a medium difficulty question. You're given two strings of the same length, S1 and S2, and a string base str. We say S1I and S2I are equivalent characters. For example, S1 is ABC, S2 is CDE. Then we have A is equal to C, so the index of the first character and the index of the first string and the character of the first index of S1 and the character in the first index of S2 are equivalent. B is equal to D and C is equal to E. Okay, equivalent characters follow the usual rule of any equivalence relation. Reflectivity, symmetry, where you can switch the order, and transitivity. If A is equal to B, B is equal to C, therefore A is also equal to C. For example, given the equivalence information from S1 ABC and C2 CDE, ABC and AAB are equivalent strings for base EED. A, C, D, and AAB are equivalent strings of base EED because does E equal A in this case? E does equal A because E equals to C and C is equal to A. AA and D should be equal to B. Okay, that makes sense. Is the lexigraphically smallest string. So smallest means that since characters have a natural order to them when represented in ASCII, A is by definition then smaller than B and smaller than all the other characters. And yep, it should be obvious. Return the lexigraphically smallest equivalent string of base str by using the equivalency information from S1 and S2. Okay, so if Parker is equal to S1, and if S2 is equal to Morris, and base string parser, why? Because out of M and P, M has to be the smallest one. Out of A and O, A is the smaller. Out of R and R, out of R and R is the smallest, but R is also equal to K, and K is smaller than R. Out of I and E, E is the smallest, and out of R and S, we already said that K is the smallest. Okay, so it seems to me like the way to approach this question would be to create almost like a disjoint graph where different subgraphs, joined subgraphs, represent characters. And the characteristic of a subgraph would be that there is a character within that subgraph or subcluster that is considered the smallest amongst those characters. And let's see, hello world, out of H and W, H is smaller, E is equal to O, but O is also equal to D, so D, L, out of L and R, L seems to be the smallest, and out of D, D is the smallest. Okay, so, yep, there we go. These subgroups, and each one of these subgroups has a characteristic that one of these characters is the smallest. So, okay, when it's a subgroup question, when there's a when the question involves some sort of graph of connected elements where there's almost like a disjoint graph involved, then there's something called the union find structure that basically allows you to quickly in O1, so in constant time, add elements to a subgroup, but then also in constant time, or maybe in n-log, no, in constant time, it lets you join two groups together. Let me show you how to implement a union find, and I'm pretty sure that this will be using a union find. So this is a dictionary where key is a value, key is a regular element, and value is the parent of that element. Union find involves two methods, union and find. Find is actually the first one that we're going to implement. Find takes a element and returns, in our case, an integer. And here we say that it would be self union find set default. Set default means if x is absent out of this dictionary, then add x with the value of x. What this lets us do is we will actually be returning x here as well, but in the case that x actually already exists in the graph, we actually want to find its most deep parent, and in that case we do if x does not equal its child, which is self, or its parent, uf x, then we're going to say that x is actually equal to find, and find its parent, self uf x. So the way this works is when we are trying to find an element, if it doesn't already exist in the graph, then we add it, and this element is called the leaf element. Its characteristic that's different from all the other elements is that its value is itself. And here we're saying that if this is not the case, if there actually already exists an element x in the subgraph, then we're going to essentially find its most deep parent as such. So if there already exists a key with x, then we just return it. Otherwise, find its parent. The other method that we're going to find is union, or define. Union. It takes an x, let's call it a and b. It does not return anything, I believe. But what this does is we will say x, find a, and y, find b. Let's call this actually f and s, first and second. And what this is going to do for us is when we want to append another connection to our union find type data structure, we will first find if any of these characters actually already have a parent or a leaf node. If not, then the leaf node is going to be itself. But then we're going to join those two disjoint graphs. And the way we're going to do that is we're going to say that, and this is actually where the problem requires us to to think, I think, or to modify the original union function, we're going to say that if f is smaller than s, so if the parent of the first element is smaller than the parent of the second element, then we're going to say that self union find s is equal to f. So we're going to join these two subgroups with the characteristic that f will always be, or the smallest element will always be the last leaf in here. Oh, sorry, I didn't add this here, but else is self uff equals else. So we're finding the leaf node of of both of these subgroups, which actually is a way to characterize these two subgraphs, and then we're joining them, because union is a join between two different subgroups, right? So this is the way that we're going to join them. Now the rest of the problem becomes pretty simple. We call union on all of the pairs of characters. So the way we do that is for fs, first and second, in zip. Zip is a method to parse strings one by one that are of the same length. So this will be the first character of S1 and this will be the second character of S2. We're going to call union on F and S. And once we've went through and created all of these different subgroups, now all we have to do is say that for C in base str, so for C in character, the base character, the base string, we're going to find the characteristic that that defines this subgroup, right? The one character that actually defines this whole subgroup. So in this case, it's going to be A, because I can just tell. In this case, it's going to be, well, LP isn't even part of the base string. But out of D and M, we see that D precedes M, so D is appeared here instead of D. So yeah, let's make a string answer. It's an empty string, and we're going to say answer plus or equals find C. And finally, return ans. Okay, let's run this. Accepted. All right. Let's see if this was a short video. Sweet. Okay. So yep, this is the correct answer. Let's look at some of other implementations, I guess. So actually, the way that I've been doing this is trying to find an implementation that differs from mine, and this seems to be one of these instances. I have an adjacent collection, so I have a collection of dictionary of it's a dictionary collection of key int value list, and I initialize a overloaded one of these dicts. Smallest map is going to be probably the okay. So this is completely different from our approach. This is also different. union join, they call it, but more appropriate is union find. Yeah, so I see that pretty much closer to the 90th percentile, people are using this union find. I'm wondering why it's so much faster. Let's look at this one. It seems to be doing pretty similar things. Def find. Find is a method that actually does the exact same thing as our find method, with the exception that it doesn't set the character if it doesn't exist. So find C, while roots, which is an element, while roots is not equal to C, so while so while the value, oh, I see what they're doing here. They're turning characters into just, they're turning the union find dictionary that we had into an array of length 24 or of length 26, where the index is the character, where the index is, for example, 0 is A, B is 1, and the value of that element is probably the parent. So this is the same union find, only they're using a different structure. Let's see, here what they're doing is populating the roots array in such a way that, see, so ord A would return, like, I believe 48, because that's the index of A in the ASCII table. And if this was A, it would be index of, if character 1 was A, the index would be 0. And it's saying find, A. What would that mean? That R is what? R is an integer, so if R1, I don't understand how this is linking the two subgroups together. We find the character, the index of A and the index of, let's say, B, which would be 0 and 1. And then we're saying that if 0 is greater than 1, which it's not, then, oh, then link these two together. So then in B's case, A would become its value. So when then we do a find or a join of all the base string characters, or when we try to replace the base string characters with the real minimal character of the roots list, we get its leaf node, which is actually the smallest character. I think that this is a completely acceptable solution, and in a sense, this is doing the exact same thing that we are doing, except they're saving on, I guess, the creation of the dictionary. So they're not doing dictionaries, they're using an array. Yep, so pretty much even the solution of union find seems to be like the proper one, and I'm going to stick with it and call it a day here. So sweet, thank you for listening. See you next time. Bye-bye.